Ladies and gentlemen, so today we're going to look at operations on functions. So chapter 9, which we're going to do most of before we finish the year, but we're going to get to trigonometry before we do all of it, has lots of issues related to functions. Of course, we've been studying functions the whole year. We've looked at the library of functions. This unit that we're going to be doing pieces of on and off has different parts concerning how to combine functions, how to operate with functions, how to invert them eventually, how to deal with functions that are composed of multiple pieces. What if you have something that's half a square root function, then it turns into a parabola, and then it turns into a sine wave? So that's eventually what our goal is to get to all those different issues with functions. So today we're going to learn how to combine functions, how to look at the different possible basic operations on functions. So I wanted to start by looking at the notation of how that works. Notation is a guide. It's there to help you. If you understand it clearly, it's like an aid to help you when you get confused in certain times, especially in calculus. Like if you know notation and you're still a little confused on problems sometimes, the notation will get it done for you. So this is kind of where that starts right here today. So if you have a combination of functions where you're adding them together and you want to create the sum total, f plus g of x, how do you think you do that with the two pieces, f and g? You add the pieces, right? So this should come as no surprise. It's not a big shocker that you get f plus g of x, okay? Okay, so what if you have two pieces and you want to subtract them? How do you think that would go? How do you think you want to get the combination f minus g, the result f minus g? You'd want to go you'd want to do that, right? So it's as simple as you might expect. What's this say? How do you read this? Multiplication. So you read this as the result f times g of x. Yeah? So that's, of course, from taking f of x and multiplying it by g of x. So most of these are, pretty simple things. But this is important for how computers work. And we're going to take this to higher level operations soon. A little bit in this class and more in future classes, okay? So we've got to make sure we've got the basics first. So how do you think if you want the combination f divided by g? Yeah, it's just f of x divided by g of x. So you guys are probably asking yourselves, why is he spending so much time talking about notation here? Well, because these are the technical things that go into how computers work and stuff. So we got to make sure we're clear. And just so it's not too uninteresting, I'm going to throw in one more. This one might be new, and this is probably the most important one in computers especially. This fog thing, people like to call this fog. This is a new operator symbol. So what does it mean? Well, if you see this operator symbol, what does it mean?
The G inside the F.
Yeah, exactly. So Michaela has seen this. She says that you put G inside the F. So notationally, you want to use the notation to help yourself first. So let's use notation. This means F is the outside layer, and G of X is the inside layer. I don't even think I need to simplify it more beyond that. That notation's really clear, isn't it? That says g of x, do it first and put it inside f of x. And what you want to remember about all of these situations is I have it written for two functions only. Do you think there are times when you can, this is what's called nesting or composing functions. Do you think there's times when there's more than two layers that are nested inside of each other? Well, yeah, there's times when you have 7 layers or 1,000 layers, and you can nest those inside of each other. So one of the little programs I have my calculus students write at the beginning of the year has to do with nesting something inside of itself 100 times, 1,000 times, and having the computer do it rather than, of course, a human being doing it. Having it do it inside of itself multiple times. This is when we watched that Fractals film. They were talking about the process of iteration. You guys remember? They were talking about self-similarity and how the computer would have to do it thousands, millions of times. This is the basics of how that works. So, new operation, what did I call it? I called it two things. Let's get that in our notes. I call this function composition. That's one of its names. I used another word associated with birds. I used nesting functions that are layered on top of one another. Okay, so those are the two words you should know for this. So let's actually get to some examples, all right? Okay, so some examples of function composition. So I tried to pick a variety. Can you guys tell me what kind of functions do I have on the board? What is f? Can somebody tell me? Parabola. Francine's got it. Hey, we'll count it. We'll count it. What is g? Line, mx plus b, right? And what is h? Good friend from a while ago. That is an exponential growth function. Yeah? Growth because 2 is greater than 1. It's been shifted left by 1. Okay? So we'll review exponentials another day. So let's see. So first, our first combination that they asked for is to take function g, the line, and subtract the parabola. So how's that going to work? Well, just write it down. Didn't we just go g minus f? Right? Yeah, this says g minus f, not just sum of f. Right now I'm only subtracting sum of f, only the 3. I've got to, or excuse me, only the x squared. I've got to distribute that negative, so be real careful. Don't make that algebra 1 mistake right there. So make sure you just subtract all of f, not just part of f. And then it's just combining like terms, right? So this is a real simple one. So let's write it in descending order. That's the way polynomials, parabolas get written, right? We got that, we've got these guys, and we've got these guys. So there we go. That's the combination g minus f for those functions. Okay? So pretty boring on that one. F times g. How's that going to work? We could follow the notation first. I recommend that. You can skip this step, of course, but you should always have it in your back pocket to pull out because notation is key. Notation is king to helping you later on. So maybe even now. So this time we're going to take the parabola and multiply it by the line. I think you guys should come pretty naturally that this is going to be an expansion or FOIL-ish type of process, right? Yes, ma'am?
Didn't you forget the square root of 6x?
Yeah, totally. Thank you, Ms. Miller. Keep me honest. All right, so when we expand this, how many terms are we going to get initially? 6. 3 terms times 2 terms is 6 terms. Some of them might combine. Let's see what they are. This one's going to be 12x cubed, thanks to Miss Miller. This one's going to be negative 18 x squared. So now I'm done with the 6x squared. I'm going to move on to the x. For these I have negative 2x squared. That's that one. And I got to do this one. That's plus 3x. I'm going to cross these off as I go. And then I've got the 12, so I'm going to have what? Minus 24 x's and plus 36. We have a couple like terms in there. Should be old hat for you guys by now. These guys are the same. And those guys are the same. 3 minus 24 is negative 21. Okay. So I can totally teach this lesson to Algebra 1 if you're not aware of that. Yeah, I mean, like, all you need to be able to do is distribute. What we're mainly focused on here is the notation of this combination thing that we're doing. Okay? Nakash?
Factor. Yeah, that's what was the first one. Yeah.
Can we factor the first one? Ah, you guys have the factoring reflex. Very nice. I didn't bother to even check on this because I knew I was just going to be expanding eventually and nothing's going to cancel out, right? What about this, though? Over here, f divided by g is going to be, of course, f divided by g. This time we've got the parabola on top and the line on the bottom. You're like done right now unless you remember, oh yeah, like we just did rational functions, and when you see things like that, you should see if they factor. Does this one factor? This is one of those tough factoring problems. I'll do it over here on the side. So we've got 6x squared minus x minus 12. 72. Any multiples of 72 that'll give you 1? 72 is like 9 times 8, right? That one. 6x squared minus 9x plus 8x minus 12. What they share, 3x. What they share, 4. Yes. Those share that whole quantity. Here's what's left. Factored. So notice, I did that kind of quickly, right? Because I think that's like the 4th or 5th time in class I've shown you how to do this. So practice it and you should be good at it. So I think there's a couple ones like that in your assignment, which is good because it's good to practice that little algorithm. This time it's nice to factor because why? These parts, since this is multiplication, get to cancel, right? That's just 1. If we graphed this combination, there'd be a hole at wherever that's 0, which is 1.5 if you solve it. We've been just talking about that kind of stuff. Right? Okay, so this simplified to a line, pretty sweet with a hole in it. All right, let's look at one more combination with these guys. And then we'll switch to some new functions. I want to give you guys a few examples. So what do you guys think? I'll let you decide. Let's put one of these inside of each other. And then let's use the exponential function. What should we put inside? You want to do hog? Oh, that's what, I was looking for that. Love it, Jason. There we go. So, hog. What should I do first? Use the notation. How's it go? What's really inside of what here? Since G's second, it's inside. And when you write this down, the sizes of your parentheses and stuff will help you if you use them. Make big ones for the outside layer. Make small ones for the inside layer. Something like that, yeah? So we're putting g of x into h. So we're going to put g of x, which is the line, into h. So now I'm going to take this, pretend I'm like one of those little machines that grabs animals and always gyps you out of your money, and go and stick it over here. Okay? Yeah, I'm bad at those. Simplify, see what you get, and you're done. I think we've got 2x minus 2. Ooh, that'd be good to graph, just for review. If we wanted to graph this bad boy, this exponential, it's got a sneaky transformation, and I want to see if you guys remember how to graph it. What do you have to do first to graph it? Yeah, very nice. You have to factor this 2 out up here. See, I'm hoping you're developing that factoring instinct because it's useful for solving parabolas, it's useful for polynomials, it's useful for transformations, it's useful all over the place. You're having that factoring instinct, you know what I mean? So this guy, you should be able to look at and say, hey, they share 2. I'm just going to factor it because that's the instinct you need to have to say what this thing really does. This is an exponential growth function because of this 2, which is shifted because of that minus 1 where? To the right by 1. So it would be like this, growing, something like that. And it'd go through what point here? 1, because anything with 0 powers 1. But instead of this being here, it's been shifted right by 1s. This whole thing would be like right there instead. That 2 is actually a horizontal compression. I'm just not going to even draw it. It's hard to draw things, so pretending it's not there. Okay? So let's do one more combination like that. So we did hog. What other one should we do?
Gog.
What is it?
Gog.
Gog? Okay. Let's go gog.
G-O-G.
I like it. You know what? Let's. I'm gonna change it. I'm sorry, man.
Wait, what's 2?
I'm going for FOF. Because I wanted to have more slots to plug into. You know, I'm bad at that game. I need more chances. Okay, that's what I'm saying. So I need more chances. So the first thing you can do is go, well, all right, notation, right? Putting f into that f. So here's how it looks with the notation. F of x is the parabola. And I've got to take that parabola, grab it, and drop it where? Into the parabola x containers, right there and right there. This says f of that stuff, so you got to take all that stuff, come over here and drop it in any of the x positions. So we've got 6 times the whole thing. I'll color code it even for you guys. So There's that 6. Then I'm putting this stuff into it. And what do I have to do with this stuff? Square it. I'm not going to simplify this one. And then I'm going to go minus that stuff. And then I'm going to go minus 12. So if we were going to simplify this one, we'd have to distribute this minus. And we'd have to go square this thing, and then after we were done squaring, we'd have to multiply by 6. Squaring this would be a pain, right? We'd get 9 things. We'd have to simplify those 9 things, multiply whatever was left by 6, and then combine with more like terms. It's not a hard problem, it's just a time-consuming one, if that makes sense. So we'll leave it there for this time. How come you can't square root it, Akash? Because there's no other side. You're not solving. You can't just square root something. You can't do something arbitrarily to a side, like square rooting, unless you do one thing. There's only one thing you guys know how to do if it's not an equation, and that is use a clever one. Clever ones don't change you. There's actually another thing you can do as well, but let's just leave that off. Okay, let's look at some other functions. Okay, so this set of examples, they're all parent functions. They should be pretty easy. What's the first one? A line, right? It's got a y-intercept 1 up 3 over 1. Just a shallow or steep line. Shallow or steep? Steep up 3 over 1, right? Okay. X cube's a snake, right? Like this. And 1/2 to the x is exponential decay because the base is less than 1. Okay? So this time we're plugging in actual numbers. This is what you'd actually do in any kind of actual situation. So let's plug in 4, the combination fog. How do you think I should start that? There's different ways to do this, by the way. There's not just one way. I think notation is where you should start, though. So go and change the notation. You guys can still see, right? I'm using big parentheses for the outside layer. So f of g of 4, that says what to do first. Order of operations says to do inside parentheses first, right? Do the insides first in general. So we're going to do the insides first. So this says put 4 into g. So put 4 into g. So you can show as much work as you want. It's up to you. 4 into g. I think we can just do that, right? What's 4 cubed? 64. And now that notation tells you what to do next, right? It's all notation. 64 now goes into f. So we're going to take that and drop it over here. 3 times 64 plus 1. Might need your calculator. 3 times 6 is 18, so 180 plus 12 plus 1.
193.
Use your calculator there, though, yeah? Okay, so how about this guy? I think we want to do notation. Didn't follow my own advice. I'm going to make my parentheses bigger, the outside layer. Then I'm going to put 2 where? F, right? It says put 2 into F right there. So I'm going to go ahead and do that. I can show my work or not. 2 into F.
6 plus
6 plus 1. That's 7. I don't think I need to show my work there. It's pretty easy. 7 I'm going to put into H. Yeah, I'm just going to show that one. So 1/2 the 7th power. So 1 to the 7th power is 1. 2 to the 7th power, power tables, or count. 2, 4, 8, 16, 32, 64, 128. Okay. This guy says put in -2. So if you're watching the video right now, I'd recommend pausing it and trying this one out. Why don't you guys try this one out? Alright, so how do we do? First I'm going to put -2 into H, right? The notation's already kind of done here. So I'm going to say, alright, G g of, if I put negative 2 into h, I'll show my work on this one. That's 1/2 to negative 2, which is indeed 4. Why is it 4? Negative exponent means flip. So 1/2 flipped is 2. Square it and you get 4. Yeah? So then we're putting 4, we're taking it and sliding it up into this position. And that's 4 cubed again. We've done that one. 64. Okay, done. This guy, first I'm going to work with the notation. So I'm going to say G is the outside layer, big parenthesis. Then F is the next layer, middle-sized parenthesis. Then H is the inside, the very inside. And I'm going to be putting in 2 into H. So first I'm putting 2 into H. So I take it and I put it up there. What's 1/2 to the second power? Square it and you get a 4th. So we're going to have G F of 4th. That means we want to put 1/4 into F. Go slide it up into the line. And you get 3 times a 4th plus 1. Simplify, that's 3/4 plus 1. How many fourths is that? This is the kind of way you want to think about those fractions.
7/4.
It's 7/4. Why? The common denominator is 4. You guys just did a whole bunch with rational functions, so you could multiply by 4/4 here, right? That's the way you were taught in elementary school and stuff, I'm guessing, is to go 4/4, yes? Here's a better way to think about it. That's good. Another way to think about it, though, is we want fourths, right? There's 3/4. How many fourths fit into one pizza if you cut it into 4 slices? 4/4. So you got 4/4 there, 3/4 there. 7/4. If you think like that, trigonometry is going to be a snap. That's like the hardest part of trigonometry right there. I think anyway. If you can get over that, you'll have it. So we want to put 7/4 into G.
That ends up being...
Those tests are power tables. 4 cubed, 64. 7 cubed. So was it?
Okay, so I will.
Was it 243? That sounds right to me. See, that's testing me too. I think it's right too.
It's 340.
343?
So, you had 43.
It sounded right. So you said 43, and I was like, I could buy it. Yeah. So that's good. That's good if you've got that. All right. I think that's good for that one. Let's do one more set of examples. Okay, so I thought I would show you a different kind of example. So, the ultimate goal beyond algebra and geometry is to be able to combine information in numerical form coming from algebraic symbols, the stuff we've been concentrating mostly on this year, things like functions, information in lists of data, things like a table of information like I've given you on this problem, and things that are pictures, in other words, graphical information, like our library of functions that we've also been working with a lot. And you should be able to take that information as a picture, as a list of information, or as symbols, and work with it in any of those 3 forms. So I thought for one of the first times we'd look at that today. So let's look at function composition or nesting in terms of a table instead of algebra. All I know about these functions is a few values in the table. I don't know exactly what their algebraic functions or their pictures look like this time, okay? So some of these might not even come out. They might not even exist. They might be undefined. Let's see what happens. So fog. If I'm going to do fog of 4, you guys know the first step you should write it down, not plug it in. Now you can plug 4 into G. So do we have a value for 4 and G of x?
Yes. -7.
That's right. 4 G of x is -7. This says f of -7. Now put -7 into f. -7 into f is 4. There's the answer. Let's try this one. G of h of -7. First we're putting -7 into h. Here's -7. Put it into h. We get
0.
Put that into G. You get pi. So you guys can see without algebra, this is probably even easier, but the concept is exactly the same, and this is the way computers work. So if I put 0 into f and then put it in again, let's see what happens. Well, you still get 0. Well, I put it into f the first time, and for this f I get 12. Another f might be totally different. Now I'm putting 12 into f. So I get 144. So maybe f has something to do with like squaring. Maybe it's a parabola. I don't know. It's behind the scenes. I can't see it. Yeah. So let's try one more. Hog. So I'm going to go h of g of pi. So when I put pi into g, I get 4, and then I'm supposed to put that into h. So I get the square root of 3. Notice the numbers in this chart don't have to be nice numbers. They can be irrational numbers like root 2, root 3, or pi. They can be anything. They could be names of people. They could be formulas. They could be cats. I love cats. They could be anything like that, okay? So let's try one that's random. I cooked these all up to come out kind of nicely. Let's find one that might not. Last example for today. You guys have your assignment posted on Moodle. So I'm going to start us out with something we actually have, like 4. And I kind of just wrote these randomly, f of g of h. Let's see what happens. So I have f, and then g, and first I need to find h of 4. I think we can do that. What's h of 4?
H of 4. The square root of 3.
Square root of 3. So that says f of g of the square root of 3. Now for square root of 3, do we have information?
No.
No. So at this point, I got to say this is undefined from the information we have, or I could do what Jacob's suggesting and create another column. You guys saw me doing it, right? When I constructed this a second ago, I was looking at it and thinking ahead, and I was going like, what numbers will I need? What numbers will I need definitions for? And that's how I did it. So that's why I was adding extra columns. That's why my chart is bent, because I was adding extra columns as I go, as I was thinking like that. Does that make sense? So at this point, we're just going to have to say, unless we are cheat and add extra information, this is undefined. Has no existence from the provided information. Okay, that's what undefined means. So going back to rational functions, when you're finding vertical asymptotes and things like that, undefined means it does not exist. It has no mathematical definition. You can provide it a definition in some cases, like this one that's very creative, but in function land, it's much harder to do that. Okay?